All right, folks. So we were talking about, I brought last few slides just to quickly review what we were talking about because we're going to use those equations. I want to go over a couple more examples. Now we were talking about curvilinear motion, right? The motion of a particle on a path that is not a straight path, pretty much, simply put. And we were using tangent normal coordinate system. Now, in that coordinate system, we looked at it. Basically, the coordinate system is defined by two unit vectors, ET, which is always tangent to the path, and EN, which is normal to path, and as a result, normal to ET, and is always pointing toward the concave side of the path. Now, in that coordinate system, we defined velocity. Well, we said velocity is always tangent to the path, so VET or DSDTET. S being the displacement or the location, sorry, of the particle on the path, along the path, basically. We defined acceleration. We said acceleration is not like velocity. Acceleration actually acceleration has two components. One component is tangent to path, like AT as we call it, is dv dt, derivative of velocity with respect to time. And the normal component is v squared over rho. Rho being the radius of curvature, meaning that if you look at a specific part of the path, rho being the radius for that part of the curve. And v just being v, the magnitude of velocity. And now we can write this as ATET plus ANEN, AT and AN being tangent and normal components of acceleration. And quickly mention the relationship. Hopefully, we'll get to do one example of finding the components of acceleration and velocity in tangent normal and basically find the equivalence in Cartesian coordinate system. It's nothing but just decomposing those vectors into a different coordinate system. And we mentioned about a special case, which is circular motion. In circular motion, pretty much the same story. The curve in this case is just a circle. So we know the radius of curvature. Radius of curvature for circular motion is basically just the radius of the circle. And velocity would be r omega. Omega being defined as angular velocity of the motion of the particle with the unit radian per second typically, or whatever angle over time. Now, tangent component for acceleration when we are dealing with a circular motion or a motion of particle on a circular path, we said is r alpha, r being again the radius of curvature, in this case the radius of the circle, alpha being the angular acceleration. And it also has a normal component. So normal components v squared over radius of curvature, in this case is r, radius of a circle, and r or r omega squared. And I also briefly compared straight line motion with motion on a circular path. And I said, well, the same way we define velocity in that case, we define angular velocity for a circular path, originally for a motion on a curve. The same way we define acceleration for a straight line motion, we define angular acceleration for a motion that is on a circular path or on a curve. We said basically that's nothing but derivative of angular velocity. And the final relationship between velocity, acceleration, and position, we have the equivalent of that in circular motion. All right. So I went over two examples. I want to go over a couple more examples today. We'll see how things go and if we get a chance to talk about this third type of coordinate system. So let's start with an example. In this example, we have actually we have a centrifuge, but let's just start with this. Suppose, as I said before, I go over examples I use in class are typically problems from your textbook at the end of that chapter or at the end of that specific section. I leave examples solved in the textbook for you guys because they're pretty well explained. So those are going to be added solved problems that you can use aside from whatever we go over in the class. Unless there's a special example that I feel like it's good to talk about in the class, I typically leave them to you to use those examples as extra practice problems. All right, suppose that you want to design a medical centrifuge. Basically, centrifuge, for those who don't know, is a pretty simple device in medical, I guess, facilities. You've probably seen it. Um, they put some samples of liquids there. It has a pretty high speed. It rotates, and as a result, it rotates the fluid samples within it. And because of the high velocity and the centrifugal force that you'll talk about even when we talk about force, it separates fluids with different densities. And even if there is some solid in it, it separates them. And well, that has applications in medical procedures. All right, so design a medical centrifuge to subject samples to normal acceleration of 1000 G, pretty high acceleration, right? Okay, so if, part A, I think, if the distance between the center of the centrifuge to the samples is 300 millimeters, what speed of rotation in RPM is needed? Right, so remember, we want to get to the normal acceleration of 1000 G. 1000 G, that doesn't really change. But then in part A, we say, well, in order to get that acceleration, we are given another piece of information that we know the distance between the center of centrifuge to samples, which basically the radius. From there, we want to find out what is the rotational speed in RPM. So let's just go over part A then once we're done with it. So if you think about this as a centrifuge, you're looking from the top, and let's say it's rotating this way. Doesn't really matter in this case, doesn't really mention. This is the center, and this distance, it's given as 300 millimeters. Now we want to find this omega. All right. Now, as usual, we start from where we are given the most information. So we know the normal acceleration, right? This is given right there, the normal acceleration, AN. And we also know this 300, which we can call it, refer to it as R. So it's pretty much the circular motion we're looking at. If I go back to what we had for circular motion, normal acceleration, that's pointed at right here, right? Normal acceleration is v squared over r, or r omega squared. I know an, normal component of acceleration. I know r, in this case. As long as you identify parameters correctly, the rest is pretty straightforward. You can find omega. So right there, we'll see, you say an is given as 1000 G. R is given as 300 millimeters. right? Which is let's move everything to change everything to SI 0.3 meters. So AN is R omega squared, right? We just care about the magnitude. The direction is obviously AN is in this direction. But in this case, we only care about the magnitude. If you want to write it as a vector, this would be R omega n En. But as in terms of magnitude, it's just Rm. It just I'll write it this way. I just An is R omega squared. Now from there, you can find omega, right? Omega is square root of An over R. So square root of An is 1000 G divided by R, which is 0.3. And that'll give you angular acceleration. Now, this everything is in SI system, so as a result, this would be an SI unit, which is basically radian per second. Right? The number would be you will get as 180.8 radian per second. Now we're asked to find this in revolution per minute, RPM. Right? RPM is basically revolution per minute, stands for RPM. So RPM stands for revolution per minute, meaning that number of revolution, if you think about a circular motion, how many times you rotate around a circle in 1 minute. A number of revolutions per 1 minute. 1 time, 2 times, 10 times, 100 times, then it's going to be 100 revolution per minute. So how do we convert this? We have omega is equal to 180.8 radian per second, and we want to convert this to revolution per minute. Right, let's put it here, revolution per minute. How do I convert this? Have you done this before? All right. So in order to convert radian per second, go ahead, Craig.
Oh, you multiply by 60 over 1 to get minutes, and then divide by the circumference.
Exactly. Thank you. All right. So we basically say we want to go from second to minute and radian to revolution. Second, well, we'll just do the multiplication. We say 60 seconds is 1 minute, and then multiply the radian per part. One to convert radian to revolution, right? So 1 revolution in a circle, it's the circumference, which is basically 2 pi. You can think about not the circumference, but it's better to not better. It's correct to say, well, if you think about 1 revolution would be basically just going this way, let's say starting from here and ending here. So 1 revolution, let's put it, I have to cancel things out. So 2 pi radian is 1 revolution. And that'll give you, if you cancel out the units, well, you have to write it in a way that you can cancel out the units, right? Second with second, radian with radian, right? So 1 revolution is 2 pi. That's what you always do. So 180.8 times 60 divided by 2 pi. Whatever comes out of this, that would be your revolution per minute. All right. That number will be 1730, and I just write it as RPM, revolution per minute. This is what we were asked to find. This is speed in revolution per minute. Just wanted you to be also comfortable with revolution per minute. You'll see it way more than you would like, I would say, especially if you're dealing with the designs and specific pamphlets in the industry, or you're trying to work on a project industry. RPM is very common, revolution per minute, way more common than radian per second. All right, so this is we got what we wanted. All right, now, that was part A. Now part B. Let me write part.
Is it?
Yes, Sama, go ahead.
Sorry. For the normal no, for omega.
Mm-hmm.
You didn't do any conversions for the acceleration or the R, right? It's just 1,000 divided by 0.3 and then square root of that.
1000 G. So G being 9.81.
Okay.
So that's pretty much but that's what we are given, right? The problem statement there basically is 1000 G. That's
Got
also
it.
something else that you would see a lot, that they refer to acceleration as a coefficient of G.
All right. Thank you.
Mhm. G is an acceleration, right? Meter per second squared. So anything multiplied by that still gives you a value for acceleration. Just a different way of referring to the value of magnitude of acceleration. All right, so let's look at part B. Now, in this part, we are told that if you want, still talking about the same centrifuge, that the normal acceleration is 1000 G. If you want the centrifuge um, to reach its design speed in 1 minute, right, what constant angular acceleration is required? This one is a little more tricky. Now you designed, right? Now you, for 1000 G, you designed your, with this radius, you designed your centrifuge, and you say, well, this is the speed of rotation, right? 180.8 radian per second, or in RPM, 1730 RPM, revolution per minute. Now the question is, how do you get, how much acceleration, angular acceleration, you need to give to this centrifuge to go from zero, right, when you turn it on? This is the design constraint, that you want to get to the speed, design speed, in 1 minute. So you know how long does it take. You are given how long should it take to get to this speed when you turn this on, turn the centrifuge on. You know what the speed is you should reach. You start from zero, beginning, turn it on. This is the speed it has to reach in 1 minute. So we are looking for something that the relationship between angular velocity and angular acceleration and time. That's what we are trying to figure out. So we know, we know that at the beginning when you turn it on, I'll call it omega naught. Initial velocity, angular velocity, is 0. Final velocity, if I represent that omega f, let's say, is 180.8 radian per second. The time that we want the centrifuge to reach to this design speed, 180.8 radian per second, is 1 minute. Let's convert that to second right here, 60 seconds. Now what we're looking for is, what is the alpha? What is the alpha you need, angular acceleration you need to reach that speed in 1 minute. If you go back, here is what we are looking to use, or we need to use this equation right here. Right? We know omega, we are looking for relationship between, this should be, actually, no, not this. This is going to make our life a little difficult. We are going to use the definition of alpha right there. It's actually easier. Why would we use that? There you go. Alpha as angular acceleration is the derivative of omega with respect to time. So d omega is alpha dt. Right? Once you know how omega changes and what is the time range, and you know alpha is constant, you can actually find alpha from there. So what I'm trying to say is, if I write alpha is equal to d omega dt, right? Just move things around. This is going to be alpha dt is equal to d omega, and then take integral. Omega is changing from 0 to 180.8. Alpha is constant. You can take it out. Actually, you can write it this way. It's just a constant, so you can take it out of the integral. Alpha dt. Now dt is changing from 0 to right? Yeah, 0 to 60 seconds. I got lost for a second. So you can calculate alpha from here. Right? That'll give you alpha is equal to this side. Maybe I don't skip. So alpha t from 0 to 60, right? That would be multiplication, is equal to omega from 0 to 180.8. If you do that, then you'll get alpha is 180.8 divided by 60. I just did the, again, I skipped, I guess, another step here. So 60 times alpha is equal to 180.8. So result alpha, we can find alpha. Alpha would be, angular acceleration would be 3.01 radian per second squared. Leave it with that unit. You're not even asked to go for a specific unit. So just leave it as that. All right, so I just use the definition for alpha, angular acceleration. So d omega dt, and then plug in all the information I had from the design velocity I had. Remember, it's a design process. So now you know the final angular velocity. You want to design, let's say you want to use a specific motor to make sure that has enough capacity or torque, can provide enough torque to reach, to make sure that your centrifuge can reach the specific speed in 1 minute. You need to find the you're asked to find the angular acceleration for that. Then knowing the angular acceleration, a little bit more calculation down the road, you can actually probably pick the motor that you can use to make sure that your centrifuge reaches this speed in 1 minute, in 1 minute. All right. So question on this one, right?
I have a question.
Go ahead, Jess.
Can we use the formula like omega is equal to like omega naught plus AT? Like,
So formula omega is equal to omega naught plus alpha t, you mean this one?
yes, that one.
Yeah, so this formula comes from this integral, right? You can use that if you're comfortable with that. This formula comes from the fact that this becomes 0 to t dt is equal to omega naught to omega d omega. If you take this integral, this gives you alpha t is equal to omega minus omega naught. And you move things around, you get omega naught is equal to, right? Omega is equal to alpha t plus omega naught. Yeah, you can use that if you actually prefer just knowing alpha is constant, so you can use that equation. just remember that that equation can only be used when alpha is constant, right? Because alpha is out of the integral. But yes, the answer is yes. We can just use that. All right. Let's take a look at the next one, next example. Now in this one, just gonna wait a few more seconds if any other question. All right. Generally, my advice is get comfortable with integral form of the equations. I know probably a lot of you remember these from physics. But what we learn in physics, or you learn in physics, maybe you've seen it before, is mainly good for when you have constant accelerations. Either it's angular or it's linear. Integral forms are useful when these are not constant. I looked at some of the quiz, results of some of your submissions for the quiz, and I realized some people made that mistake that they assume the acceleration is constant. They use just the typical equation for constant acceleration, and made mistakes there. Right, the whole thing went wrong. So it's good to keep in mind that acceleration is not necessarily constant all the time. Right? This is that's what the integral form. That's why it's, I would say, more useful, because you can always remember that you're making this assumption that acceleration is constant. You take it out of the integral. In typical equations you had maybe from before, those equations were derived based on constant acceleration. But that's not the case all the time, unless you're told directly that the acceleration is constant. All right. So next case or example, we have, well, we can think of this as so we have some kind of a combustion engine or some crankshaft mechanism, right? The crank AB is rotating with a constant counterclockwise velocity of 5,000 RPM. So find the velocity of point B. I'll draw a schematic of the problem. I'll show you where point B is. A, in terms of normal and tangent components, and B, in terms of Cartesian components. All right, so we basically have, I can draw the schematic here. Let's say this is the piston inside cylinder. Try to, let's say, the cylinder with some kind of, this is fixed, and then this is connected to this part, and let's make it, draw it in a way that it doesn't look like 90 degrees. Let's draw it this way. Can do maybe a little better. this is, yeah, let's go with this. All right, and these two are aligned, so if I can draw a dotted line, it's as good as I can do. This is where the center rotation is, and we have a rotation in this direction, counterclockwise. I don't know if clockwise and counterclockwise are useful anymore these days. People, maybe most people are wearing digital watches, so dealing with watches, digital watches, so or clocks. But just make sure that everyone is on the same page. Clockwise, when you hear clockwise, is this direction, and when you hear counterclockwise, is in this direction. All right, it's always the case. All right, so this is point B. This is point B that we're talking about. This rod is connected to the piston. So when this rotates, I'll call this OB. When OB rotates counterclockwise, the piston inside the cylinder goes down, right, all on the left side. When it comes to the right side, the piston starts going up. So piston goes up and down. OB rotates around O in counterclockwise direction. Now at this given moment, and here is your also XY coordinate. This is X, this is Y. Now at this moment, well, I have to follow the notation I mentioned in the problem. Since I refer to this as A, let's go with A. Right. Crank AB. At this moment, this crank AB is rotating with a counterclockwise angular velocity of 5,000 RPM. So we know that omega, I refer to it as omega AB, is, since that's for the crank AB, just to identify that. But generally speaking, this is your omega, and this is your omega. If you don't want to go with naming, things are confusing, just look at the drawing. So omega is 5,000 RPM. Now what we're trying to find is, you want to find the velocity of point B. Right? So what was the velocity? At first, pay attention that this is a circular motion. Right? If AB, well, it's a constant, it has a constant length. So you can think about that as the radius of the circular motion. Now that is given, I have to add that also to the problem statement. This length here, I draw it in a way that now I'm stuck. I don't have enough space there. So we'll put omega there. And then this length is 5 centimeters. So 5 cm. So B is rotating around A with the radius, well, the distance between A and B is constant. You can think about this as a circular motion. That is, if you think about the full motion, that's something like this. So B is rotating around A, R being the length of AB, and it follows a circular path. Now, we want to find the velocity of point B. Well, we know the angular velocity, omega. If you go back to circular motion, when we talked about circular motion right here, right? I said V is R omega, and it's always in the tangent direction, the direction that is tangent to this circle, right? And the direction of the V, well, it depends on the direction of the theta, the way you are moving. So if you're moving counterclockwise, which is actually the case even here, this is basically counterclockwise. It's going in this direction. You'll get the V in this direction. If you were going clockwise, you'll get the D in the opposite direction, the V in the opposite direction. So V is always tangent to the path, obviously, You only have one component, and the magnitude is r omega. Now, if you go back to what we have here in this crankshaft system, or this crank AB, B is following a circular path, AB being the radius r. So that'll give you, well, let me write everything. So r in this case would be 5 centimeters. And the direction for your velocity, if I want to draw it here, would be like this. Right? It's tangent to the path. Let's try to, there you go. This is your V as a vector, if you want to think about it. And remember, this tangent to a path is perpendicular to normal to a path. So this angle here is 90 degrees. Just be aware of that. Normal to a path is from the point you're studying towards the center of rotation. That's normal path. Your radius of curvature r is 5 centimeters. Tangent to a path is basically your velocity v. Your v is tangent to a path. I don't want to make it crowded there, but this would be E. Of course, I'm running out of color already. So this would be E T. This would be E N. Yeah, I don't know if I made it better or worse. Probably you're saying, yeah, you made it worse, Masood. But all right, so ET and EN, right? Now we know V and we know omega and R, so it's pretty straightforward. The only thing that we have to do is that make sure that everything the same system of units. So 5 centimeters would be 0.05 meters. We have to convert that RPM. We know from before, to convert from RPM to radian per second, you just have to multiply that by 2 pi over 60, right, to convert minute to second, and revolution to radian. Right. So since I don't have that number, I'm just going to cheat and I'll write it this way. So VB, let's call this VB since it's the velocity of point B, would be R omega. And R omega, since I'm writing it in vector form, ET. You multiply, you do this multiplication, you get 26.18 ET, meter per second. Right, let me just identify that as one thing you wanted to find. So this is the answer to part A. In terms of normal and tangent components, so we found it in terms of normal tangent. There is no normal component for velocity. We already know that. Tangent component 26.18 ET, or 26.18. Yeah. Now part B, oh, this is part A. Now part B says, well, good, you found it in tangent normal component system, normal tangent or tangent normal coordinate system. Find it now in Cartesian coordinate system. Cartesian coordinate system being x, y there. Now let's see what we got there. If I draw it here, since I made it very crowded there, this is x, this is y, this is x, and this is your x, this is your y, and then you have your v somewhere. Let's draw it in different color. You have your v somewhere here. I'll try to be some reason something happened there. All right, I think I know what happened. All right. So this is v. Now your v being this is vb. So I have to find the component of this vector in xy coordinate system. It's pretty much just decomposing a vector and finding its component in xy coordinate system. So if I draw this as this line, this is this one, and I'm missing out the good important piece of information there is given in the problem statement. I don't have to be worried about that. You probably were thinking that how do I find that? This angle here. theta. Theta is given as 45 degrees. So if I know this is 45 degrees, it means this angle here is also 45 degrees. So much for making it less crowded. All right, so how do I decompose that? How do I find VB in Cartesian coordinate system? I know VB is there. VB creates a 45-degree angle with the horizontal axis, or x-axis. You can think about an axis parallel to x-axis. So VB would be, what is the magnitude of VB? 26.18 times cosine 45 degrees to find the component in x direction, right? This would be, if this is, this would be Vx, or VBx, probably better to say. This would be VBx, and this would be VBy. I know that angle 45 degrees, so in that right triangle, just pretty much decomposing the vector. Cosine 45 degrees, it's to the left, so there is a negative there. And then I have 26.18 sine 45 degrees. And that's also downward, so it's also negative. And this is I, this is J. So this is going to be the representation of your velocity in Cartesian coordinate system, XY coordinate system put there. I just decomposed that. Now, remember, this is velocity, so we are talking about a derivative with respect to time. We don't care if the velocity is exactly at the origin or anywhere else. We just find the components in different directions. We don't care about that initial offset. If it was position, it mattered, but velocity, in terms of velocity, it doesn't matter. You take derivative with respect to time when you find velocity, so that's irrelevant. So that becomes, well, I use the magnitude from there, right here. This, I know the magnitude, I have a vector. I know the magnitude, I know it's the angle it creates with horizon or horizontal line. I decompose that into an XY components. And obviously, whatever we get in X direction is I, whatever we get in Y direction is J. Right? So pretty much once you find the, remember, we are still studying this same motion. Right? And what changes is that we are just using different coordinates system. We can either represent this specific vector. Vector is the same. The velocity doesn't change. Physics of the problem doesn't change. Right? The physics is the same. What changes is that we just change the way we represent that velocity. Now, this velocity can be represented in tangent normal coordinate system, or can be represented in Cartesian XY coordinate system. So it by the end of the day, once you find one, you should be able to move to the other one. It's just a matter of representation. It's not a matter of velocity changing. All right. All right. Let's do the second part. Add something to this problem. Let's say we also, so question about this part first. All right. So let's say we do the same thing for acceleration. Let's say it's a little more, just a couple more steps, but this, pretty much the story is the same. Let's say the acceleration, let's say find, I'll just write it this way. Also, find the acceleration of point B in terms of, obviously the same story. Tangent normal and Cartesian components. Tangent normal components. Let's just make sure that they're separate. Tangent normal components and Cartesian components. Right. So same story we follow. Right? The acceleration pretty much is AB has two components typically, as long as none of them is zero and we have both, can have two components, AT, ET, right? Component in tangent direction, plus AN, EN. I'm not bringing these from some random place. We've talked about this, right? This is pretty much what we had here. We said AT, ET, AN, EN. AT, AN would be R omega squared or V squared over R, depending on how you want to present that, and AT being R alpha. So it's just a circular motion. I'm using what we learned before. Okay. So this case, I'll just write it this way. AT is R alpha. Now, what is R alpha? What is alpha? Do I know alpha?
No, you don't know alpha.
All right. Look at the problem statement. First line, what does it say? Yes, it is zero, exactly. Because we are told that it's constant, right? The constant counterclockwise velocity. So when the velocity is constant, it means acceleration is zero. If the acceleration is not zero, acceleration is what changes the velocity. And when you have acceleration, you're either increasing or decreasing the velocity. So if velocity is constant, well, what is acceleration? Acceleration is derivative of velocity with respect to time, right? Either in linear or in angular, circular motion. Doesn't matter. Anywhere. When this is constant, the derivative of a constant value is zero. When velocity is constant, the derivative of constant value is zero. So acceleration becomes zero, either linear or angular. In this case, we're talking about angular motion, so we're talking about angular. But when you're dealing with this motion on a straight line, let's say, you're told the velocity is constant, same story. So this becomes zero. And that is because acceleration is, let's say, constant velocity. So alpha is zero, constant angular velocity. So now we'll just then go to our normal component. AN is R omega squared. Now, that we can calculate, right? Or V squared over R, depending on which one you want to use. V squared over R. Now you can use both because you know what value magnitude of V is. You know what omega is. So either of these work. That'll give you 137. I think so. 707 point. Let me double check. Yes, 13707.85. That would be your meter per second squared. Remember, the whole motion is angular motion, but each component, you look at each component as a linear, typical acceleration, right? The unit is SI unit, meter per second squared. So if you have this motion right here, and let's say we have, let me just draw it here. You have your point B can have two components, right? If this is the center of rotation right here, can have AT and AN, right? AT being along ET and AN being along EN. So that's the component of acceleration in normal direction. So at the end, your acceleration in tangent normal coordinate is 13707.85 En. This is going to be your acceleration in normal tangent coordinate system, tangent normal coordinate system. Now again, you're asked to convert this into Cartesian coordinate system or represent that in a Cartesian coordinate system. The same story, you just decompose this vector. All you do is that now you have a vector in normal direction, in this direction, pointing from point B to the origin of your Cartesian coordinate system. And you can find just the components. So if I want to explain this probably better, right now, this is where you are. You have let's see, your circular motion, you just have a normal component there, pointing towards, I could probably draw something better. It's not really that much of a, bear with me there. All right, so let's say this is your normal component. Hopefully that is pointing to center. This is the center. This is point B. This is your AN. And here is your Cartesian coordinate system. And this is X and Y. X and this is Y. So same story, we just decompose this. All right, let's do it this way. This is 45 degrees, which means this is also 45 degrees. Now, what you can do is that pretty much you have a vector. So A, B in Cartesian coordinate would be, or what was the magnitude? Magnitude was 13707.85, I think. 13707.85. Let me double check. Yes. All right. So now you have to decompose this vector. You know it. You know the magnitude is this 13707.85. You just have to find the components. Again, the danger of making things crowded there. I'll just draw it here. This would be AN in X direction, and this would be AN in Y direction. So the first one would be this value multiplied by cosine 45 degrees in I component in X direction. It's positive, so I'll leave it that way. The second one would be 13707.85 sine 45 degrees. But it's downward, so it's negative, and it's in Y component, Y direction. So this becomes the representation of your acceleration in Cartesian coordinate system. Acceleration in Cartesian or XY coordinate system. All right. Question on this one. So, as I said, it doesn't, you are finding the acceleration and velocity. Right? You're talking about position, velocity, acceleration. Remember these three things for now. The coordinate system is just there for you to make your life easier. As you see in this case, the representation in Cartesian coordinate system where XY has two components, where the representation in normal tangent coordinate system has only one component in normal direction. Right? So it's probably easier to represent in normal tangent coordinate system. But by the end of the day, it's the same acceleration. If you find the magnitude, of this, I can write probably the final values here. I have 9692.91 I minus 9692.91 J. Well, sine and cosine of 45 degrees are the same. So this is probably the final answer, not the previous one. I should. The magnitude is the same. If you want to find the magnitude of this, right, you say AB is equal to square root of whatever is the first, this one squared plus whatever is this one squared. The magnitude of this should be the same as the magnitude of this one. And the magnitude of this one is, oh, just that, 13707.85 meter per second squared. And you should not forget to put the unit here, 2 meter per second squared. So the magnitudes are the same. They're just representing these vectors in different coordinate systems. That's all. All right. One coordinate system could be superior to the other depending on what kind of problem or what kind of situation you're dealing with. But at the end of the day, it's just the way we represent. Right? That the concept or the magnitude or the value of acceleration, value of velocity, they don't change. Right? All right. Let's see. Let's do another example. This time, let's do something that is not on a circular path. Let's do something that is on it's a curve. I'll wait a few seconds if any question on this one. All right. Hopefully no question means everybody followed. Which is always not a good conclusion to make. But, all right. So next example, well, it's a very simplified version. Let's say we have a rocket, like say let me draw it here maybe first, so I keep space for drawing. Let's say this is obviously not some object you can think about as a rocket that is flying, let's say, or moving in this direction. The problem statement says the horizontal component of acceleration is 6 meter per second squared. And the downward acceleration component is G, well, which is basically 9.81 meter per second squared. The velocity of the I'll call it center of mass, but don't be worried about that. Center of mass, G, which is basically right here, basically you can think about it as the velocity of the rocket, along the 15 degrees direction of its trajectory, G trajectory, is 5,364 meter per second. For this position, find A, the radius of curvature of the flight. B, the rate at which the speed v is changing, I guess, is changing, should be a good, changing. And C, the vector representation for the total acceleration in tangent normal coordinate. So here's the situation. We have this, and then you can think about the path, a path that this is, let's say this is the path, and it has the velocity, acceleration in this direction, 6 meters per second squared, and the acceleration downward of g. Now also you're shown that this is the path, so this is the center of this path, this as O, and this is your radius of curvature, rho. And this angle is 15 degrees. So much information there. This angle, I exaggerated the angle so we can draw there, but this is 15 degrees. And we're given the velocity in that direction, so we know what velocity is in that specific direction. Here is the velocity. You're told that this is 5,300. Let me not write it here. I'll just call this V, and I'll represent it here. This is V. A lot of things going on there, but at the end of the day, we'll see it's actually not that complicated. So, get a sense of the problem. This rocket is following this path, like curve. At this given moment, we know the acceleration in horizontal direction is 6 meters per second squared, and we know acceleration in downward direction is g. And we know the velocity of the center of mass, the velocity of this object, this rocket, is 5,364 meters per second along the 15 degrees, along this path, which creates a 15 degrees angle with the horizon, the horizontal direction. So this is actually nothing but basically decomposing a bunch of vectors. Now, think about this now, that you are going from Cartesian coordinate system to normal tangent coordinate system. This is your, maybe a different color. This is your EN, and this is your ET. Tangent, normal. And then you have your Cartesian 6 meters per second x direction, g in y direction down. Remember, if that angle is 15 degrees, this angle is also here is also 15 degrees. So here's what I do. I know the components in XY. I can find the components in tangent normal. You see if you follow. See if you follow. AN in normal direction, or component of acceleration in normal direction, would be 6 sine 15 degrees negative minus 6 sine 15 degrees. And G value, cosine 15 degrees, but positive, plus 9.81 cosine 15 degrees. I have 6 in X and G in Y. I want to go to En and Et, right, in normal and tangent component. Looking at a normal component, if I want to decompose that, that 6 should be multiplied by sine 15 to get the Y component for that 6, or En component. And 9.81 should be multiplied by cosine 15 to get the En component for G. AT is a, I don't know what it is. Same story. Now I have to decompose two vectors, or find the components of 6 meters per second squared and G, these two vectors, along tangent axis, tangential components, or along ET. That would be 6 cosine 15 degrees. It's in positive ET, so keep it as positive, plus 9.81 sine 15 degrees. It's also in positive ET. The G component, forget about En, now look at ET, and you're finding the components of acceleration 6 meters per second squared and G along ET. If you do these, you will get 7.923 meter per second squared, and this one becomes 8.33 meter per second squared. So I basically, instead of previously you had one vector going from one to another coordinate system. You went from normal tangent to xy. Now you're going from xy to normal tangent, but instead of one vector or one component, you have two components, 6 meter per second squared and G downward. Yes, you can think about it that way. Exactly. You're taking it as, I just didn't want to make it crowded there. Let me put it here. So we can take this as x, and you'll take this. Let's see if I can do it x, and take this as y. All right. Now, good point. Maybe I should have put it there. Now we have normal and tangent components, right? The rest is pretty straightforward. Once you have that, look at part A. It's asking you to find the radius of curvature. Well, radius of curvature, we know AN is equal to V squared over rho. Remember, this is not a circular motion anymore. This is a motion on a curve. Right? Going back to when we were talking about motion on a curve, here we are, this one. AN is V squared over rho, rho being the radius of curvature. So I know V, right? I'm given the value of V. I know now what AN is by decomposing those components, so I can find the rho. So radius of curvature is V squared over AN. V squared over AN, well, V squared is V is 5364 squared divided by AN, which I found as 7.923. Oh, you do this math, you will get 3631 point, actually it's larger than that. 361, I don't know, I'm making 3631 31515 meters. So large radius, obviously. If this is a rocket, this is the altitude. That's probably too large. So it's part A. So radius of curvature. Part B. The rate at which the speed v is changing. Right? Basically, this is asking us to find dv dt. The rate at which the speed v is changing, dv dt. Now, what is dv dt? Yeah, sorry about moving between the slides. I just want to show you where we talked about this. If I go back, dv dt right there is at. I know what at is. Right? So going back, this is basically just is equal to at. I found at. At is 8.33 meter per second squared. So that's part B. Part C, that's where I started. I started from part C to make it easier for A and B. But pretty much this is what we already found. This is the vector representation for the total acceleration in tangent normal. That's what I did. All right? A is equal to A T E T plus A N E N. Now AT is 8.33 ET. This is 8. Plus 7.923 EN. So it started from part C, kinda. I decomposed the vectors to make my life easier. You could start from the beginning, a radius of curvature. Then you would have realized you need AN. For part B, you would have realized you need AT. All right, so you have to calculate AN first to find the radius of curvature for part A, and you have to calculate AT to find dv dt for part B. And once you get to part C, you already know what AN is, you already know what AT is. You write the acceleration in terms of tangent and normal directions. All right. All right, I'm going to stop here. I will talk about polar coordinates in next class. I'll see. I'll probably go over two examples there, and then take things from there. All right.